This video is all about conversions. Being able to convert from a number of moles to a number of liters to a number of grams or to a number of particles or vice versa. So after you're done watching this, you should have a decent idea on how to do dimensional analysis. So dimensional analysis is just a trick in mathematics where you're trying to change the units of one number into the units of another number. And that's really all it is. So there's a lot of conversion factors. You've probably done this before in the past. You've changed over centimeters to inches. You've changed over meters to kilometers. You've done this type of work before. So this is just involving chemistry units. So you've also done something like this in a math class where you just have to figure out how many dozen are found in 64 eggs. Why you have 64 eggs, that doesn't matter. Just how many dozen are in 64 eggs. Well, you have to first recognize, well, what's the conversion factor for every 12 eggs for any dozen in general. For you would need 12 of whatever your object is. So if we're going to talk about eggs, you need 12. So if we have start with always with what you have. So if you have 64 eggs, then our unit is egg. Generally, we don't make our units plural. So start with that, multiply by the conversion factor. We want to convert eggs into a dozen. So we put the unit that we want in the numerator of our conversion factor. For every 1 dozen, we need 12 eggs. So we put 12 eggs down below. Again, we do not make it plural. And then we just multiply it through. First, you cancel off the units that you don't need. So egg disappears. Then you just do some math. 64 times 1 dozen divided by 12, or just simply 64 divided by 12 will give you 5.3 repeating, which in reality means you have 5 dozen with 4 eggs left over. But if we're just looking at pure mathematical, you have 5.3 repeating. That's really all you'd have to do. And you've done similar stuff like that in a math class. So in your work booklet, you probably have this mole conversion chart, and that tells you all the different conversion factors that you need in order to work with these units in chemistry. On the left, you have your volume of a gas. So again, I'm going to stress this is a gas at standard temperature and pressure. That's what STP stands for. So the conversion factor to go from a mole of individual particles to an actual volume of a gas, you would actually take this top route. All right, you would go up this top little part right here. I just drew a line there, and you'd have your multiplier factor. I'll look at it right here, just off to the side. So I rewrote them there, 22.4 liters per mole. And that's what you actually have there circled in red. If you wanted to take a certain number of volume and convert it into a number of moles, we would just go down and follow the arrows. Start from volume, go to moles, we would go down. And we multiply by that conversion factor, which over here says it's 1 mole for every 22.4 liters. So those are just the conversion factors involving volume. If you want to deal with representative particles, so that means you should probably write this down on your little workbook here. If you're working with individual elements, so again, that would be like your lithium, just Li, if you will. You would have, it would be, your number of particles would be called atoms. If you're working with ionic compounds, so that would be lithium chloride, for instance, you'd be dealing with formula units. That's what the particles would be called. Even though it says particles here, you have to be specific for the type of individual particle that you actually have. If you're dealing with molecular compounds or diatomics, individual diatomics, you'd have to call them molecules. So even though it says particles here, you have to kind of know these 3 terms. Usually in the question, the terms are given to you, so there's no memorizing really that needs to be done. So the conversion factors are written down depending on which way you're going to and from. So they're written right there, retype them out. If you're going from a number of particles, so a number of atoms, if you will, to the number of moles, you would just go down that chart. You'd multiply it by the appropriate conversion factor. If you were going from the number of moles to a number of individual atoms or formula units or molecules, you'd have to take that bottom route and you multiply by its conversion factor. The last one is your mass conversion. Now, the mass conversion, you'll notice inside this little thing that I typically call a flux capacitor because it looks like the flux capacitor from Back to the Future. There's no number next to the mass unit there or there. It just says G for grams. I typed in an X there and there. That's mainly because we don't know what element or compound that we're talking about. And so therefore, we don't know what the actual mass is in grams. So this is yet to be determined. It's to be determined by every individual element or compound, but it follows the same idea. If you want to convert from mass into a number of moles, you would just move up this chart, right, and multiply it by the appropriate conversion factor, where X is the actual molar mass of whatever you're dealing with. And likewise, if you're trying to find your mass given a number of moles, you would just go down this chart, right, and multiply by its conversion factor. And I'll do a few examples, probably 6 examples, one of each type, just to give you an idea of how to do this. So always keep this thing handy, or just memorize these, whatever works best for you. So for instance, if we have 5 moles of sodium hydroxide, how many formula units do you have? So we're starting off with 5 moles. So we're starting off right here in the center. Okay, so always write what you have to begin with. So 5 moles of sodium hydroxide. And I stress this out because it'll make a lot more sense when we start doing stoichiometry. Write down the actual compound as well. Right now, it's just sort of dead weight, but if you get in the habit of always writing down the compound, doing stoichiometry will be a bit easier in the following few days when we actually start doing it. Up until then, it's just going to be dead weight that your teacher is going to make you do no matter what. So starting off with what you have. You have 5 moles, so write down 5 moles. Always start with what you have. Then recognize, well, if you're starting with moles and you want to go to how many formula units you have, so that is your, again, your represented particles. See, I said you didn't have to memorize it. You just have to know that formula units means a particle. You just multiply it by the conversion factor that's on your chart. So you multiply by the conversion factor. So instead of writing down the word particles in the conversion factor formula, I write down formula units, so FU to abbreviate. So I multiply by Avogadro's number, 6.02 times 10 to the 23 formula units for every mole. And then I do a quick little cancellation of units because the moles cancel out. And then just do some math. 5 times 6.02 times 10 to the 23 gives you about 3.0 to 2 significant figures times 10 to the 24. So again, keep track of your actual significant figures. And that's all there is to it. How many moles are found in 2.44 times 10 to the 23 atoms of copper? So we're given our atom, we are given our number of moles. They want to know how many moles. So they want us to go down to the center. Starting off with a certain number of particles, so atoms, we would take the path to the top right. So start with what you have. Always write what you have first. 2.44 times 10 to the 23 atoms of copper. So I'm not going to write the word copper when I know I could just use the periodic table symbol. Figure out the conversion factor. So again, we're going from the top right down to the center. So put in that conversion factor equation, right? 1 mole for every 6.02 times 10 to the 23 atoms. Cancel off the units that cancel off. So the atom cancels, the atom cancels. You could technically cancel 10 to the 23 and 10 to the 23. That would work too, but some kids don't like to do that, especially when the number here is different than the number here. So be aware that could come up. And you just multiply it through. And you guys can easily do that with your calculator. I will kind of put a little word of caution. Depending on what calculator you're using, when you put in your scientific notation, you might want to put parentheses around that, depending on how you do that inside your calculator. Otherwise, you might run the risk of some students end up taking the 1 and then they'll hit divide, and then they'll type in 6.02 into their calculator. Then they'll go times 10 to the 23, and they write it like that. Sorry, writing with a mouse here. Your calculator will do this first. Some of your calculators will, and then do that last, and you're going to get basically wrong math in the end. So just be aware of how to enter stuff into your calculator. And don't be afraid to pause this video at any point in time if you're not getting, so you should be working these problems through kind of at the same time. If you will, pause it after every problem, make sure that you can actually calculate the numbers that you see on the screen in front of you. And if you're having way too much trouble going, oh, I can never get the same thing you get, send me an email at any point in time, and I can try to fix that from there. Next, third question, how many grams? So we're going to do a mass here. How many grams are in 7.20 moles of dinitrogen pentoxide? So dinitrogen pentoxide looks like that. We're looking for how many grams. So that tells us we have mass. How many grams is a mass? So let's start off with what we have. We know we have a certain number of moles, and we know it's dinitrogen pentoxide. Determine where you're going. So since we're starting off with moles, we're starting off at the center, and then we have to figure out our mass. So we look at our conversion factor. Our conversion factor is going to be so many grams per mole. We just don't know what that is yet because we have to still determine our dinitrogen pentoxide. So you might want to write it off to the side or just do it all in your calculator. But if you write it off to the side, you recognize you have two nitrogen atoms. So we multiply 2 times 14.01 grams per mole. You have to add that to our 5 oxygen atoms, so 16.00 grams per mole. Add them together, multiply them, then add them together, and you should get 108.02 grams per mole. Okay, so then you put that into your conversion factor. All right, so you want to make sure that's in there. And then, of course, cancel the units that cancel. The moles cancel out. The grams don't. And the compound doesn't either. So then you just do some quick math. 7.2 essentially times 108.02 will give you about 778. I simplified it to 3 significant figures since I have 3 significant figures in my actual starting number. And I'm not going to consider the significant figures of the conversion chart because it's just a conversion chart. Okay. Next example. So how many moles are in 922 grams of iron 3 oxide? So rust, if you will. So we are looking for the number of moles. So this time we are looking to go to the center again, but we're going to start from the mass, which means we're going to, I'm out of place here. So that means we need to go up to the center. All right, whenever we have this. And so we have a conversion factor where we have 1 mole over a certain number of grams. We just don't know what that is yet. So you have to determine what iron 3 oxide is. So in order to figure out the molar mass, you have to be able to write this compound down. All right, if you can't write down iron 3 oxide, you should probably go back a few pages or to last week and try to review how to do some ionic compounds. So iron 3 oxide, you basically have 2 moles, or 2 groups, if you will, sorry, not moles, 2 groups of iron. So 2 times 55.85 grams per mole. You've got 3 groups of oxygen, so 3 times 16.00, and so that gives us 159.70 grams per mole when you multiply, then add them all together. Okay, so then you put them into your chart, into your conversion equation. And that part would go in the denominator. So if you're wondering why I don't have per mole here next to the grams in the actual equation, because technically I'm just doing 1 over this. And because I have a per mole in the end here, that just flips up to the top, and then I just end up with 1 mole over the 159.7 grams. That kind of just took care of itself. So that's, if you're wondering that why I write it grams per mole here and then just grams there and put the mole up there, that's pretty much why. So cancel the units that cancel, the grams cancel off, so the mass unit cancels, and then you just do some math. 922 times 1 divided by 159.7, and you'll end up with, to 3 significant figures, 5.77 moles of iron 3 oxide. So that's how you do that. Second last equation, or not equation, example problem. What volume does 0.6 mole of sulfur dioxide occupy at standard temperature and pressure? Once again, if you see STP, it just means standard temperatures and pressures. So we're starting off with moles. So write out what you have. 0.6, I kept the 2 trailing zeros because they are significant. So we'll just keep them in there. So we have 0.6 mole of sulfur dioxide. We want to know what the actual volume of that is. So we will multiply with this conversion factor. So multiply by 22.4 liters per mole. So that's the base definition of Avogadro. He determined that the number of mole of a certain amount of gas would actually have 22.4 liters. So cancel off the units that cancel, the moles cancel, and you're left with just a quick multiplication, 0.6 times 22.4, and then just carry over the units that don't cancel. Oh, I goofed in my typing. That should have been a liter. I must have made this too quick. There we go, I fixed it. I'm not editing that out. We all goof. So yeah, 0.6 times 22.4 will give you 13.4, and that's liters, because the liter here did not cancel out. That liter did not cancel, so that's what I should have for unit there. I don't know what happened when I was typing that out. I must have fallen asleep. So the last example, how many moles are in 33.6 liters of helium gas at standard temperature and pressure? So we are going from liters. So we have liters of a substance and we want to convert it to a mole. So we're going to the very center. So multiply by the inverse this time. So again, we're using the bottom conversion factor, 33.6 liters multiplied by 1 mole, then divided by 22.4 liters. The liters will cancel the appropriate units, and then we should be left with 33 divided by 22.4, because again, you can just ignore 1. You should have 1.5 moles of helium. So that was quick. I probably went through that a little bit quicker than what I would have done in class, but I know you guys can pause this stuff since it's on YouTube and rewatch certain things and try the problems. There's not that many of them. And if you have questions, again, just send me an email. Answers, I believe, are just at the bottom of this page here, but I don't have that posted on this screen capture. Okay, you have a good one.